right, so one of the big things in Calc is being able to interpret information. So we use the trigonometric identities to manipulate our equations. And this is great practice at being able to substitute, manipulate, identify, and almost kind of memorize. So each of our trig functions, and there are 6 of them, have a reciprocal. And up on the board, you'll see, and in the packets of notes, I gave you those identities. Most of them should be something you've seen before. The quotient identities are also something we've seen. We know that tangent is really a variation of sine over cosine. And the reason for that is in physics, when you talk about a tangent line or an object going tangent, you're actually talking about the object's vectors, and their vectors are sine over cosine, because sine is the y's and cosines are the x's. Last year, when you looked at your unit circle, tangent was a variation again of a line that represented the rate of change or the slope of that trig function. So tangent is a word we're going to use a ton in Calc, and it's always going to represent or be in correlation to sine over cosine, which is a variation of slope. These 3 down here at the bottom are big. You need to know your Pythagorean identities. The Pythagorean identities in trig come from the Pythagorean theorem. Oh, I never handed you your papers, Tim. I'm so sorry. I was waiting for the papers to print because I ran out of papers. Here you go, honey. You're welcome. All right, so those identities you need to memorize. And you can almost see how those identities are the Pythagorean theorem, right? Pythagorean theorem is a squared plus b squared equals c squared. If you look at each of those identities, sine squared is kind of like your a squared. Cosine squared is kind of like your b squared. Sorry. And the c squared is your 1. We talked about yesterday that the unit circle means it has a radius of 1. Well, if you think about the triangle, that c value, that hypotenuse is representative of your radius. And that's why the Pythagorean identities all contain the number 1. Because they were all created and constructed with respect to the unit circle. So all of those 1s are kind of like representing the radius. It is important to recognize that we can manipulate the Pythagorean identities. The Pythagorean identities are not locked in, and we're going to talk about that in 2 slides and what I mean by that. We talked previously in our packets about even and odd. So the identities in trig are even and odd identified as well. So you can see if you plug in negative x for sine, the negative comes out in front. So if the negative goes in and comes out in front, is sine even or odd? You put in a negative, so let's take a little walk down memory lane. If you put f of negative x in and you get negative f of x, is that function even or odd? It is odd. So that was like letter E, I think, on our packets, even and odd functions. So if you put in a negative u here and you get a negative out in front, sine and cosecant are odd functions. If you put in a negative x and you get the original function back, then it is even. So cosine, tangent, secant, and cotangent are even functions. The cofunction identities have to do with the unit circle again and talking about all students take calc and being able to know if I'm looking for the sine of 120 or the sine of 5/5, where do I subtract it from? And that's from the cofunction identities. So in your packets, we have letter S. Letter S is about verifying identities. So these bottom two slides are simply hints and helpful ways to do that. So one of the ways I said was that you need to be able to manipulate the trig Pythagorean identities. So if you look at example 1, it has sine squared equals 1 minus cosine squared. That is an alternative form of sine squared plus cosine squared equals 1. There are times where you are going to substitute, but in order to be able to substitute, you have to use that type of alternative form. It is always helpful, and I say always figuratively because there are times where it's not, but it is usually helpful to rewrite all equations in terms of sine and cosine. So if you start with a problem, it has like sine squared plus tangent equals secant. It helps sometimes to change the secant and tangent to sine and cosine. Example 4 is simply saying that sine squared plus 2 sine x plus 1 is really a quadratic function and can be factored. So we're going to factor trigonometric functions. Okay? So we have cotangent theta over cosecant theta equals cosine. When verifying identities, you are only allowed to change one side. When verifying identities, you're only allowed to change one side. So we are going to leave this equal to cosine theta. I want you to take a minute on your own and change cotangent and cosecant to be all in terms of sine and cosine. So you're going to use like the quotient identity and the reciprocal identity. So cotangent is cosine theta over sine theta, and cosecant is 1 over sine theta. And we know that fractions and fractions are a no-no. So what we're going to do is multiply by the reciprocal of the denominator. And when you do that, you cancel your denominator. And you'll notice that when you multiply these two together, you have sine theta on bottom and sine theta on top. And we get that cosine theta equals cosine theta. And we're happy. We have verified that cotangent theta over cosecant theta is really just cosine theta. Let's get a little bit more complicated. I am going to use theta instead of all these betas just because I hate writing beta. So we have 1 minus sine squared theta over cosine theta equals cosine theta. Once again, we're going to leave the right side as is because we want to always take complicated and make it simpler. So we're going to manipulate the left side. What do you know about 1 minus sine squared theta? Where do I kind of see that? Well, I can kind of see that in the equation of the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. If I just manipulate it a little bit. So I can say cosine squared theta equals 1 minus sine squared theta by subtracting sine squared from both sides. And then what I can do is, since this is the same as that, I'm going to replace, trade out, substitute, whatever word you want to use, the two orange boxes with the underline. Because cosine squared theta is 1 minus sine squared theta. So that gives me cosine squared theta over cosine theta. So cosine squared theta is really the same as cosine theta times cosine theta, because we know that something squared is just that same thing twice. Well, if cosine squared is cosine theta, then the exponential rule says that I can subtract the bottom from the top. So that has an exponent of 2, this has an exponent of 1, so 2 minus 1 is 1. And I get cosine theta equals cosine theta. And I have once again proven or verified the identities. We have tan theta over secant theta equals sine. So again, when you're identifying or manipulating, you always want to keep the simple and change the hard. So we're going to keep the sine theta, or sine alpha, I guess in this case. And we're going to change tangent and secant to all be in terms of sine and cosine. So tangent is sine over cosine. Secant is 1 over cosine. Once again, we don't like a fraction in a fraction, so we'll multiply by its reciprocal. Cleaning up the bottom, and then what's super nice is the cosines cancel here, and I get sine equals sine. See, I'd rather enjoy these. One, because I know I got the right answer. They always work down to match. Okay? Anytime you see a trig function squared, your first thought should be to look at the Pythagorean identities. So I see a tangent squared, I'm thinking, all right, what's my Pythag identity that matches it? And in this case, tangent squared theta plus 1 can be replaced with secant squared over secant, and our goal is to make it equal to secant, and we have 2 on top, 1 on bottom, so you cancel 1, and they match.
Xavier Batista, please come to the office. Xavier Batista, please come to the office.
All right. How are we feeling? Better? Okay, not bad. So letter T in your packets is about solving the trigonometric identities, and I showed you an example of that yesterday, where you kind of need to know, okay, what's the value coming from the unit circle, and then working backwards from that. So in this case, we have 2 sine x minus 1 equals 0. So we're trying to solve for x. If I want to solve for x, what's your first thought maybe? If we're solving for x in a normal equation, we get x by itself, right? So what would you do first, Lane? I saw your hand go up. Perfect. You add 1 to 0. We want to get that sign alone, so we sine x equals 1/2. Is that a trig value? Is there an angle that sine is equal to 1/2? Because the answer is yes. I don't care if you give me the degree or the radians, but there is definitely an x value that makes it 1/2. Anybody know the degree or the value? Or the radians? What do you think, Sarah? Not a it's not. Oh, remember, anything that ends in a 5 is a square root of 2 over 2. You're good. Flip it one more time. I think one more page. Yeah. Thanks. Isn't there like a table on that page? Yeah, it's on there. Yep. So it's 30 degrees or pi 6. And technically, how many times is the sign positive on the unit circle? Going back to all students take out. How many times is sine positive? So you gave me the angle in quadrant 1. What other quadrant is sine positive in? Yeah, over here, right? So if it's 30 degrees in quadrant 1, or pi 6, then it also lives in quadrant 2, right here, which is 30 degrees up from 180, or backwards. So 180 got 180 minus 30 is, yeah. So it's also at 150, or you're adding 1 to subtracting pi 6 from 1. So it's 5 pi 6. This next slide is really just a graphical way of saying it. So if you think about the equation I gave you sine x equals 1/2. Well, that's kind of like saying y equals sine x and y equals 1/2. So you're looking for their points of intersection. You can almost think of it as a system of equations. I'm going to run out of space because I can't write on the sides out there. So points of intersect, that works. So here's the line y equals 1/2, that dotted line. Every time the sine function hits that dotted line, represents a point of intersect. Now, we usually just look at the answers in terms of the unit circle, which is 0 to 2 pi, which are the answers you gave me. But our answers can actually live beyond 0 to 2 pi, and that's what you're seeing here, 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 and here. And that's what we can represent with these two solutions here. So if you're not given a strict domain, then truly the answer to that trig question is pi 6 plus 2n pi, meaning that we can get back to that point anytime we go around the circle. So 2 pi represents what? Does anybody remember what 2 pi represents on the unit circle? It's a nice geometry word. The circumference of the unit circle is 2 pi. So by adding 2 pi times n, where n is any number, we're essentially going around that unit circle a whole bunch of times. So here's my unit circle. Actually, I don't want to circle that many times yet. Here's my unit circle. Our first two answers lived here and here. Right? The representation that diagram gives you says that if we go around once, we end up here. I can go around twice and still end up there. 3 times and still end up here. If I go around 3 times, that's like 2 times 3 times pi. Or it's like saying pi 6 plus 6 pi. That represents that little dot right there. Still the same point. It's just that it's like walking the track, right? You walk the track outside once, you've done a quarter mile. Walk it twice, you've done a quarter mile plus a quarter mile. 3 times. So you can hit that same spot on the track and keep adding and adding the circumference of the track. We can do that on the unit circle. We can get the same solution by going around and around that unit circle. Going around and around and around that unit circle is called its period, or one cycle. Do you remember doing periods and cycles? Okay. Many of our trig equations are really quadratics in disguise. You guys know how to solve quadratics and factor them. So one of the techniques when trying to solve a trig equation is to actually solve it like an algebra equation. So here you're given 2 sine squared x minus sine x minus 1. If I told you that sine of x was equal to a, you could rewrite that as 2a squared minus a minus 1. And then if I told you to factor that, you would say, okay, I need factors of -2 that sum to -1. So I know if my last number is negative, I have one negative and one positive. I know that I need an A in both. I know that one of them is going to get a 2 and one of them is going to get a 1. I know the back numbers are both 1, because 1 times 1 is 1. So really, I just got to figure out, okay, how do I get my OI to give me -1? So if I take 2 times -1 here, I get -2. So that means my positive needs to be here. So I get +1 because -2 plus 1 is -1. So in factored form, this becomes that. But we said A was equal to sine x. So instead of using A in my problem, we're going to say 2 sine x plus 1 times sine x minus 1 equals 0. If I told you I wanted to know what A was equal to in that problem, you would set each of the A's equal to 0, right? You would say, okay, A, 2A plus 1 equals 0, 2A equals -1, A equals -1/2. I don't know if I continue this on the next slide. Oh, I did. Good. So we said that this is 2 sine x plus 1, 2 sine x. Oh, did yours go into a second slide? I'm sorry. I'm in second page. So just like if this was an A and that was an A, the zero product property says you set the factor of the front equal to 0 as well as the back. So we'll say 2 sine x plus 1 equals 0 and sine x minus 1 equals 0. Solve for sine, and we get sine x equals -1/2 and sine x equals 1. This one is way easier. When is the sine 1 on the unit circle? It only happens once. Yes, thank you, 90 degrees. So 90 degrees or pi. So in the last one, we talked about when sine x equals +1/2, and we said that was at pi 6, pi 6 and 5 pi 6. So sine x will equal -1/2 down here and over here. So in order to get to those points, you have to take 2 pi minus pi 6. That's kind of like 12/6, because 12 divided by 6 is 2. So 12/6 minus 1, or 11 pi 6. And then over here, it's 1 pi plus pi 6. So 7 pi 6. In like 2 weeks, we have a unit circle quiz. So if you don't know those unit circle values, you may want to start looking at them. We will have a quiz on the unit circle in here. You need to know your values because there will be a lot of problems where we look at trig identities and take limits and derivatives, and you need to know your unit circle. Okay, we can also look at functions involving multiple angles. So in order to solve these, we have to kind of talk about the solution set as a whole, or it's that plus 2 pi n type idea. So once again, you're always trying to identify the cosine, sine, tangent all by itself. So we're going to add 1 and divide by 2. So we get cosine 3t equals 1/2. This is a little more challenging because it's not cosine t, it's cosine 3t. So what you're going to do is you're going to kind of ignore the 3 to start. You're going to say, okay, when does the cosine equal 1/2? So we know that the cosine of t equals 1/2 when t is equal to 5/3. So in order to solve this problem, we're going to say that 3t equals 5/3, but we need to isolate t, so we have to multiply kind of both sides to get rid of that. Or we could leave it like this, but t, we divide by 3, divide by 3, it's kind of like multiply. So t is equal to pi 9. Cosine is positive in 2 spots. So we need to also get the spot down here. So that's kind of like 2 pi minus 5/3, which is 5 5/3. So 3t also equals 5 5/3 or 5 pi 9. Since there is not a restricted, so there's not a restricted domain, that means that this answer set repeats every time we go around the unit circle. So we have to add that 2n pi to our answer. The last slide, we kind of already went over that. I just gave you those identities to help you. I don't believe, I don't think this is on your packet at all, but if it was, I put it on there. It's just another identity that sometimes helps, but I'm 95% certain that's not on your trig packet. Okay.